Hello everyone! Today, as promised, we'll talk about displacement technologies in Unreal Engine 5, see how they work with our column and our layered material. We'll also discuss a few additional global functions, not related to displacement, but completing the topic of master material. For those who haven't watched the previous videos, let me briefly inform you that we're not just covering UE5 functionality here, we are making a fantasy cottage for games. We are looking at how to create architectural environment objects for games in UE5. So if you are interested in the whole process of creating environments for games from start to finish, with quite detailed breakdown and nerdy discussions along the way, consider subscribing to the channel. This video in particular is the third video covering the master material I created for this project, so I invite you to watch the previous videos if you haven't already. And moving on, first question, why do we need displacement at all? Let's go back to our column from the last video. We have here the normal maps, as you can see, of our mixed materials, and it already creates some illusion of surface depth. As graphics evolve, level of detailization in games rises. We realize that although we still need normal map very much, and it copes perfectly with small details the size of, say, a phalanx of a finger, it is probably not enough to authentically convey the topology of the real-world surface, the volume of which is measured by a whole human finger or even the size of a hand. We also make a caveat that these scales depend on how close the camera can get to the surface in the game, or what exactly is the surface. For modern days flat wall, which I have in my apartment, the normal map only would be perfectly enough. And there are still AAA games where normal map and subtle geometry is sufficient to dress the surfaces, such as top-down strategies or RPGs. Nevertheless, for first-person shooters or even third-person action, the modern player's eye would like to enjoy a more detailed picture. Probably, and that's why the normal map alone is not enough anymore. And if we compare these two columns, normal only and this intermediate version with displacement, you will see the difference, and perhaps you will want to detail your graphics richer. The second question is, what are the ways to work with displacement in Unreal Engine 5? And which of those ways are most aligned with our values for content production that we talked about in the last video? Visual quality, production speed, and performance. And performance is usually the stumbling block when it comes to displacement-related issues. We can't afford to do everything we want. First method that is much talked about, much advertised, popular amongst artists doing portfolios on UE5, is Nanite Tessellation. I'll also call it dynamic displacement. The second method, which is less talked about, is called Nanite Static Displacement Mapping. And it is, as the name suggests, static, as opposed to the first method. Here I would like to draw your attention to the documentation real quick. And there is a caveat to both of these methods. Both of them are marked with the "this feature is currently experimental" label. This means that no one takes the responsibility to 100% claim that these techniques are applicable to game development out of the box. However, I will say that studios are already using them this way or another. Studios are studying them, experimenting, and getting results, and with proper attention of technical specialists, these technologies can be quite workable. And looking ahead, taking into account what's been said, I will immediately inform you that I will use static displacement mapping, this second method, in my project. Later I will tell you in detail why and show you the difference. So there is also a third method. It is to perform surface manipulation in a third-party application. Do displacement in Maya, Blender, ZBrush, and then import fairly high polygonal models into Unreal Engine with the expectation that Nanite will allow us to save performance. However, this method is very energy intensive and quite destructible at the same time, so we risk losing our production speed. Any jumping from one application to another, too many actions and exports is always a significant waste of time, something that we would like to avoid at all costs. And since we need the displacement to work in conjunction with our blending layers, this makes ways that require working with geometry outside of Unreal Engine 5 not efficient at all, albeit possible. Also, there are other pitfalls there. I've honestly tried to get whatever the optimal process is for working with the third method, but always different circumstances prevent me from doing so efficiently. So we will only talk about and show the first two methods, but it's worth keeping in mind that for some types of assets, other than flat walls, the third method may be adequate. So I'm going to start with Nanite Tessellation, and this one is just very easy to manage and requires minimum time for production. In the last video, I didn't have time to do an overview tour of the master material graph itself, so let's take a very quick look at what's in here. It all starts with the blending mask. We've talked about it in detail, and I'm going to use the splat mask, which I'm going to stitch through the entire feature system all the way through. So what happens next? Using the material attribute layers node, we call here the already masked mixed material attributes that we've compiled by use of material layer blend, and now we are able to add functionality on top of the mixed layer system. Using the get material attributes node, I can get the data of individual material attributes I need and perform further manipulations with them separately. For example, from what we have already talked about, I take the result of blending by MNG textures, in which I store the red and green normal channels, and here in master material I restore the Z vector, the blue channel, thus sending a full-fledged normal map to the final material. Everything else that is here is just two global functions for even more variability of texturing. This one is called ZGradient. It will have to be rewritten a bit, and we'll do it later, and the other one is Procedural Snow, which will be laid by upVector function, which we will also discuss later. And let's see what happens to our displacement. Remember, from the getMaterialAttributes node, in this case I get the result of blending of the alpha channels of GRAH textures. And then look, it doesn't serve us as a displacement in the material. It is plugged into some switch parameter, height bake, and further on into the base color. I will explain why this is so when we will talk about static displacement mapping. And since we're trying Nanite Tessellation now, we will create a slot for the displacement attribute. We'll copy and paste this wire in there and make sure to enable tessellation in the general shader settings. And now we can see what we got. As you can see, everything works. The result is acceptable, but not perfect. The gaps between the bricks are not too deep. I want them to be deeper. The indentation of the chipped plaster at the same time is not so bad. I like this pronounced shadow here. We have a reference, so let's turn to it and compare. I think we're close to the reference. The plaster is a little bit much forward. We can make it thinner, although in reality it happens in different ways. Here on the old example, plaster is much thinner. I don't know how it will be better in the end, but it's not so important just now. Now, we've finally reached one of those moments that I deliberately skipped when I was reviewing the material layer function. So let's go back to it. To the very beginning, where we have our main texture and the alpha channel that contains the height map data. And as you can see, before getting to the output, this height map goes through the levels function. And this is a very simple function that simulates the behavior of the levels function from other graphic editors, such as Photoshop or Substance Designer. So let's have a look at it. And it's very simple. Just subtract, divide, and power driven by scalar parameters, and we get a very handy tool for editing black and white textures. So with the parameters of the levels function, we can edit the range and mid value for each layer separately. Let's say I want to move the plaster closer to the bricks as we discussed, and this is where these three parameters are located in the material layer menu. And in the case of dynamic nanite tessellation, I can edit height maps on the fly and see the result immediately. It should be noted that this is greatly hindered by the behavior of shadows. They break, and sometimes just moving the camera saves. Sometimes you need to rotate the model back and forth, which is not very convenient. So let's move it a little bit closer. I'm looking at this corner here. And let's rotate the model so that the shadows come back to normal. And I've tweaked these parameters a little bit more and got this result, which is pretty good. And you could add depth to the brick texture or tweak it further, but that's not so important now. So visually we get a great picture, but then what is wrong? Why am I cautious about using nanite tessellation in the project? And here is the thing. If we turn on the display of nanite triangles, we see this situation. And the triangles seem to even decrease a bit based on the distance, yet there are unimaginably many of them still, and most importantly, there are many of them without any need. I will say that I don't know if it's even worth looking at the number of these triangles and how much they actually affect performance. If you have such technical knowledge, I and everyone who watches this video and reads the comments would be immensely grateful if you could tell us how nanite tessellation affects performance. For me, a mere artist, such a sight is frightening. I, as a mere artist, having watched Epic Games presentations about nanite, want to see the triumph of virtual geometry in all its glory. I want to see my triangles, without any LODs, shrink intensely and dynamically as the camera moves away to a minimum number required to hold the silhouette of the model. And that would give me the confidence that if I were to make an entire city of such houses using displacement on every wall, I would be working within reason and within the practices technically allowed in production of AA or AAA games. And let's thank Epic Games because we have that option. And now it's time to talk about nanite static displacement mapping, which requires a bit more movement to get the result, but I think it's more performant in its design. But once again though, I could be wrong, and besides, the situation may change with time and new updates on Unreal Engine 5. First of all, let's turn off displacement, we won't need it. Let's turn off tessellation in the shader settings, and remove the slot. As you can see in material, we don't use displacement now. So how do we get it? Here we have a flat column again, and let's go to its material instance. Under the details tab, we have this height bake parameter, which I mentioned earlier. This is purely debug functionality. We need it only for temporary manipulations. We will always turn it off after use. And here's what it does. Instead of our color, we got a visualization of our height maps. And you may not agree with me, but in my opinion, it's quite convenient to customize the parameters of the levels function this way, rather than on the fly. And in fact, this allows us to edit the height maps in relation to each other, like we sometimes do in graphic editors such as Substance Designer. See, using all the same parameters, black clipping, white clipping, mid value, I can practically sculpt the surface relief within narrow limits, of course. I usually tweak the range of the height map first, with black clipping and white clipping. In this case, I want a fairly flat surface, so I'll press them towards each other. And because the range is so small, I'll use the mid value to set the overall height of the layer. And this is where the indentation, this chipping of the plaster, will be almost non-existent. So I'm going to raise the height a little bit, which means I'm going to make the color whiter. Then we can go to the other layers and adjust each one individually. I have already done this work behind the scenes, so I'll leave it as is. And in general, I will say that this work is designed to be done once for a material or even a series of materials, which will be changed in rare cases. That is, we're counting on the fact that if we're working on a full-fledged game, we will not have to come up with new levels parameters for each wall. Rather, we will simply reuse either pre-made layer stacks as a whole, or copy individual material layer instances with already configured parameters and change something ad hoc if it did not work by itself. Now back to the column. Let's assume we're satisfied with the mixed height map for this material. And now I'm going to want to bake this information into a texture. To do this, I'm going to open the static mesh editor of this column. See, now I have some other material instance assigned. First of all, I need to assign the same material instance that is assigned to the instance of the static mesh on the level. And let's do that. And now we have the same material instance in the viewport of the static mesh editor. And this is a prerequisite for baking the texture because this is where we're going to bake. Let me remind you that we have a second UV channel with unique mapping, non-overlapping, mapped from 0 to 1, which is very convenient for baking textures. Next, I go to the Asset tab and see here the Bakeout Materials tool. In the opened window, be sure to click Use Mesh Data, change the texture coordinate index to 1 because we're using UV channel 1, diffuse is what we need, and set the texture resolution to 2048 by 2048. Click Confirm. After that, the window disappears and the column material is updated and replaced by some strange newly created material instance. Important caveat, as soon as this material appeared, I immediately go to the save list and uncheck the box next to this material. We won't need this material instance. It is just a result of how Bakeout Materials tool works, so to avoid clogging up the project, it's best to make sure you don't save them right away. Nevertheless, we do need it for now. We open this material instance and here we see this texture, which is what this whole thing was about. The texture combined from our column height map layers, baked on UV channel 1. Next we go to File, Save As, and I have a special Height Bakes folder where I save this texture, giving it a proper name. When that's done, we go back into the static mesh editor of the column, remove this new material, bring back our original material instance. Next we go back into our material instance and uncheck the Hide Bake checkbox, returning the material to its original state. Next, in the static mesh editor, under the Nanite settings tab are the parameters we seek in order to bake the displacement. Here you can see the texture slot, and this is where we're going to put our bake unique height map. An important parameter is displacement UV channel. Again, we put here 1, We are interested in the unique UV mapping, which lies in UV channel 1. The parameter trim relative error, I can't properly explain its meaning in its entirety. You can read the description of this parameter in the documentation. I'm not going to read it out, because myself I don't understand the definition for 100%. I do understand it in general terms, however, and how it works for my cause. And in general terms, with this parameter I'm going to adjust the density of the mesh, the number of triangles literally. This parameter should not be 0. The smaller it is, the more polygons we get, the more detailed the result will be. I always start with 0.05, and from here I look at the situation. But in general, the range of work will usually vary from 0.03 to 0.1, depending on the task. Next, in the fallback target parameter, I set the percent triangles. My default is 2%. You can go higher, not so important right now. Again, I won't dwell on what fallback mesh is. I don't know all the particularities of how it is used in the Nanite system, and there are several use cases for that mesh, but I'll send you to the documentation for that. For my current task, it is just a good condition for static displacement baking to work expectedly. Magnitude is literally the power of displacement. In dynamic tessellation, Nanite tessellation, it is recommended not to put this parameter more than 5 or 6. For static displacement, it is probably not so important, so I can afford all 14 or even more if I would want. And of course we need the center parameter, because our mesh is not just a flat piece of geometry, it has corners. Center allows us to choose a position from 0 to 1 on our height map, which will stay in place on the 3D model. While anything darker than the selected position on the black and white gradient will be pushed in on the 3D model, and anything lighter will be pushed outwards. Normally 0.5 is used, but I want to shift the center a bit to push in more data than push out, and this will allow me to have the decent corners for my column. Once everything is set, we click Apply Changes, and after a moment we get the displacement baked onto our 3D model. The result is satisfactory, everything is displaced as it should be. Again, I have already spent time to adjust the levels of the height maps of the layers, so everything looks immediately correct, in my case. And now for the most interesting part, what differentiates static displacement from Nanite tessellation, and why I prefer static displacement. If we go into Nanite visualization, into triangles, here's what we see. Let's better turn on the wireframe. You see here, we're essentially getting a new topology. This displacement itself creates the optimal topology for Nanite. And because of that, Nanite runs pretty correctly. Look at it in dynamics. The mesh is optimizing smoothly, intensively, as efficiently as possible, as it should, right? With static meshes modeled in Maya or ZBrush, I don't always manage to achieve such a correct topology, such a uniform and at the same time optimal mesh for Nanite to consume. And here, in fact, Nanite displacement creates its own topology for Nanite system to optimize. And it looks quite similar to a scan in the end, only created by hand and fully controlled by the artist. Now let's see how the parameters I mentioned actually work in real life. For example, let's reduce the number of polygons and make the model even lighter. Let's set the trim relative error to 0.09 and see what happens. It's 32,000 triangles now. It works wonders. It works better than Decimate in ZBrush. The quality doesn't degrade that much. Even this result would be quite strong in a modern game. I will leave it at 0.05, for portfolio work a little higher will do, and the result is slightly cleaner. Now let's talk a little bit about the downsides of this process and potential risks. The first point here is of course the production time. It's still not a super fast process. Baking this texture, especially if you take into account that when you change the mask painting, you don't necessarily but probably will need to rebake the height map. It's still great that all this is done in UE5, but in comparison to Nanite tessellation, static displacement obviously loses a bit in terms of production speed. And the main problem, I think, lies in the user interface. The Bakeout Materials tool seems a bit less supported than other tools in Unreal Engine 5. So ideally, if I had the programming skills, I would just write myself a blueprint or plugin that would allow me to do all these operations in a couple of clicks. Also, you could probably make this height map texture virtual and tie this whole system to a static mesh instance on the map rather than the static mesh itself. And that would be absolutely marvelous in terms of performance. The second disadvantage is this texture, and it must be in the slot. We can't get rid of it even after we have baked it. And I have no answer to the question whether this texture participates in the shader or it is purely utilitarian and is not read by the shader in any way, but only takes up disk space. Based on the logic of static displacement, it seems to me that it does not participate in the shader and in the build as a whole, since we see real triangles and the whole topology is created by them. Having said that, it is worth saying that this process can be considered non-destructive. We can always clean everything up, put everything back to zero everywhere, and look, everything is back the way it was. We can of course use a different texture, and so do it however we want. One remark I'd like to report, since I did this behind the scenes: if we remove the displacement and look at the wireframe of the original model, you will see that I subdivided the mesh a little bit along and across in particularly flat areas. When you have two long triangles, this will interfere with the displacement algorithm, and you can get small problematic areas here and there. To avoid this, it is enough to simply split two flat polygons, judging by the eye. Let me emphasize here, it's not required that the whole mesh be somehow particularly uniform over the entire area of the model. Displacement will do this work for us, but just to help it, add a couple or more edge loops to break up the most flat and long polygons. The second topic worth mentioning in the context of displacement is corners. If you remember, I made a very thin, rounded chamfer. Here it is. In theory, and in the ideal scenario, I want to be able to keep the corner as less deformed as possible during the displacement. I want to get all the benefit of displacement on planes, but in a way that my corners look adequate. And in reality, when working with displacement, we will have problems on the corners. With this material, I seem to be able to get around them, but with other surface types, we will often run into this. For an example, let's put center at 0.4, also magnitude at 14, and after it's baked in, look at the corner. It's literally inflated now, and it's not pretty. This is a result that we need to avoid at all costs. So in the case of a relatively flat surface, as is my case, it is enough to experiment with the value of center, and it will quickly give you an acceptable result. Here, even my chipping has preserved its outlines, you see, although it is initially too tiny. You can add bumps on the corner on the 3D model itself, as in the old days, so that everything looks organic, and I will do it for sure later. But quite often, we would want to have a good sharp corners or some detailed chipping or precise damage on the corners, and in this case, experimenting with center parameter will not be enough, and the only way out is by using the edge meshes. Now, when we have very detailed geometry after displacing it, these edge meshes will work pretty harmoniously with it and integrate almost seamlessly, almost invisibly into the main mesh, even without using any alpha transition methods. In my example, on the cottage, we'll look where we can use edge meshes and where we can do without them. Perhaps on this brick foundation, I will use them to represent the logic of brickwork better. On other elements, however, we'll see. Now, if you remember, when we talked about texture color painting and virtual texture blending, I said that my problem is the lack of technical ability to work with it as I would like. Let me show you what the problem actually is. Let's connect another blending method, set texture UV coordinate index, texture resolution, and quickly draw something. One layer, second layer, one circle, second circle. Next I'm going to go into material instance and turn on my debug mode, hide bake. And as before, now I want to see this coloring on the column material itself in the static mesh editor, and that's where the problem arises. See, on the material instance itself, the column coloring information doesn't exist. It is only bound to the column instance on the level. The virtual blending texture is bound to the column instance. It doesn't exist in the material. So I can't bake this information out with this bake out materials tool. That said, again, it is definitely possible to do this, but not with out-of-the-box methods, to my knowledge. I tried to use Blueprint for baking through render target in Unreal Engine, but without success, because again, Blueprint refers to material instance and does not take into account virtual blending mask. But these are all technical issues and nuances that are good and proper to understand, but not necessary to solve for portfolio work, unless it is a technical artist's portfolio. That's the end of the displacement topic, and let's now conclude the master material topic by talking about all the additional features, some optional add-ons that can be useful in certain cases. And as the first such feature, let's take a look at what I call the outliner. It is also called border mask. This functionality lives in my material layer blend, but first let's see how it works. Let's open the parameters of the plaster layer, for example. We need the blend asset parameters, and among them we'll find outliner color and outliner opacity. I'm going to choose some contrasting shade for clarity, and when I set the opacity to 1, you can see a subtle outline on the mask of the selected layer. Let's make it black to make it even more noticeable. I also have an outliner softness parameter that adjusts the contrast and with it the area of coverage of this stroke. Naturally, where the layer is painted with more contrast, where the gradient between our RGBA splat mask layers is sharp, we will have a rather hard outline and there is nothing we can do about it. Where the gradient is softer, it works more interestingly. Clearly, we're not going to use this in such a contrasty color, so let's turn down the outliner opacity. And look, this barely noticeable tint already gives some interesting visual effect, like moisture at the edge of the plaster, slightly darkening the texture, or dirt and dark patina peeking out from underneath the chipped plaster. Look, I use it here too. Here, because of the displacement shadow and the faint tint, you can barely see the outliner, but sometimes it is in this very subtle color variation that the beauty of realism is revealed. Let's now turn on outliner in our fourth layer, the soft grunge layer. It's much more aggressive here, you see. The pattern again depends on the splat mask gradient and the height map variation. Let's tweak the opacity again. Look, this pattern resembles some salt or alkaline deposits, or streaks around the leaks, for example when the liquid dries. Again, by playing with color you can get interesting patterns. This feature is not always necessary, and not on every layer, perhaps even here it looks a bit too much, However, I hope you agree the effect is visually interesting, and I think it's a good help in texturing obtained procedurally, mathematically, not requiring additional textures. So let's take a look under the hood and see how it's done. To do this, we're going to open up the material layer blend. Right here in the frame is the blending itself. You can see I am interpolating the outline color and the base color of the bottom layer. And after that, I pick up the top layer base color and interpolate it with the result of the first interpolation, using a simple scalar parameter as the driver for the opacity. The result goes straight to the base color of the bottom layer, and after that to the blend material attributes node. But the most interesting part of the whole thing is happening in this outliner mask, which is used as an alpha in the first interpolation. And this reroute node brings us back to our height blend material function, in particular to this section of the function that I purposely skipped in the previous video. Now let's track it back to where it started. And if you remember, we discussed that in the layered material video. Here in this section we got ourselves the result of comparison of two height maps taken from the bottom and top layers textures. Later we divided it to obtain the blending softness parameter. Here I also divided separately and assign yet another softness parameter. But this one is going to serve solely for the outliner mask. This effect I showed just a few minutes ago. Then I interpolate the values of vectors in x and y, vectors with different directions, by our blend mask between layers, and it goes into alpha input. Then, after saturate, which normalizes the obtained values, putting them in the range from 0 to 1, we subtract y from x, thus getting the difference of the two masks. And this is our stroke. These numbers of vector values in the lerp node I picked up by the eye, using the texture in alpha for clarity. If you want to understand exactly how this works, the best way would be to stick some primitive mask in input alpha, like a white circle with a soft gradient on a black background, and experiment with the values. So that's how I get my layers outlined. An optional but very cheap and interesting additional texturing feature, which is always nice when working with layered material and tileable textures. Let's talk about the second global setting. I call it ZGradient. As a result of it, we'll literally get an additional color gradient, or rather two gradients, along the z-axis, that is vertically in Unreal Engine 5. The switch parameter allows me to plug this feature in, so I check the box and nothing changes. And let me explain how it works. Let's first select our static mesh on the level and go to its Details tab, down below to the Custom Primitive Data Defaults tab. And what is Custom Primitive Data? This is a very useful system that allows you to adjust some desired shader parameters at the static mesh instance level, rather than at the material instance level. Similar to how we discussed in the last video, the principles of working with virtual blending mask. The benefit of using custom primitive data is similar. It allows you to get variability without creating a new material instance, and therefore without increasing the number of draw calls. So how do I work with this? On the left, you can see the names of my parameters that I have specified in the master material. On the right, as soon as we click the plus icons, the scalar values of these parameters appear. On the column, we get this weird thing now. And there's a mistake here that I'm going to address right now. Because I repackaged the textures behind the scenes, something went wrong. I am using an outdated version of the MNG texture, so I'll remove that override, and now everything should be correct. One more thing, the last layer, the grunge soft layer, I'm going to disable it for now because again, due to the lack of MNG texture, it's shining through on top of the gradient. In the future, I'll fix this. The gradient should be on top of all layers, but for now, we'll do without these nuances and just disable the layer. So let's go back to our custom primitive data parameters, and we immediately have this pink gradient. I can go to ZGradient color and choose some other, more suitable color. Next, let's rotate our gradient so that it works along the z-axis as planned. With this parameter, rotation angle, we rotate the gradient. And look, we have two of these parameters. We can rotate one down and one up. And now we can adjust the fall-off and the intensity of one and the other. Now you can see this clearly in our both gradients. Here you can see the gradient being multiplied with some random noise that I'm loading from the MNG texture, that generic noise channel. It's roughly like this. Let's turn on lead mode and have a look at it. The effect of course depends on the color you choose. In this example, I choose a dirty brown color and it works well in my opinion. I mainly need these gradients to represent the dirt accumulated at the joins of architectural elements, but they can be used in different ways in other cases as well. Now let's copy our column just to demonstrate the beauty of custom primitive data. And look, on the new instance of the column, we can, for example, completely remove these gradients. At the same time, on the first instance, they remain as they were. That is, this texturing is in no way tied to the material instance. Let's see how it's done, and for that let's go to our master material. And here we finally deal only with the global features. Let me remind you that the material attribute layers node calls all the functionality of material layer and material layer blend, which we talked about, and it calls it here, inside master material. Then by using get material attributes, we get the attributes we need. And for our gradient, we need base color, which is the result of blending the color of all layers, and we also need our generic noise. See, I get it from the anisotropy attribute. Like I said before, I'm using some attributes here just as a means of transferring data from one function to another. If we go to the source of this generic noise in the material layer through this chain of reroute nodes, we get to the blue channel of our MNG texture. And right here is the black and white noise that we're going to use to blend with the gradient. I didn't waste much time. I just threw in the first grunge from the Megascans textures here. So we've got this grunge, and now back in master material, we're going to go use it for its intended purpose. As you can see, it's plugged into the input noise mask of a custom simple UV gradient function. Let's see what's inside it. It's quite simple and quick. First, we take the custom rotator so that we can rotate the gradient, as I did, you remember. In the input UV, I put in the UV1 index, again our uniquely mapped UVs. Yes, I'm just using the UV coordinates for this gradient. It's not suitable in all cases, but it's simple and performant. There are more interesting procedural ways to project a gradient based on the geometry of the object and its position in the world, but I decided to take the simpler route. It's worth remembering that this UV method forces us to pack the second UV channel according to the object's position in the world, which for architectural elements is usually not a big deal, but just something to keep in mind. Next, we get the linear gradient, the very basis, and then using a series of procedures, We adjust the contrast of the gradient, its position by UV coordinates. We add our generic noise to the linear gradient. And with this parameter, we adjust the contrast of the sum of the linear gradient and noise. I don't think I've shown this parameter in the example before, so let's fix that. Yeah, it's hidden here. It's a feature of the custom primitive data index system. I'll tell you about it a little bit later. And look, I can adjust the hardness of the gradient line as well. After interpolation, we added saturate to keep our black and white values within the correct range, and that's it. So what happens next? Again, in master material, the output of the function falls into the alpha input of the lerp node. And here, the old-fashioned simple interpolation between our color parameter for the ZGradient and the base color attribute takes place. As you can see, I'm not using any tint functionality, although it would work well here. Then, as you can see, I duplicate the same function and do another interpolation to get a second gradient so that I can paint both top and bottom on the same model. In short, the purpose of this effect is to save time and resources on decals of leaks and deposits of stacked dirt on the joints of architectural elements. This way we get them quickly, procedurally, and the decals will be better used for more interesting and local detailing. What else is important here? It's how the parameters themselves are organized. For example, we have a regular scalar parameter, and under it we have a comment, custom primitive data index 3. Now let me create just a regular new scalar parameter. Let's convert it to a parameter and call it something. And then in the details of this parameter, you see there is a custom primitive data tab. All you have to do is check the box and select the index. And the index will correspond to this numbering right here in the details of the static mesh instance. See, for example, our color parameter takes up 3 slots. Technically 4, but I use 3. An individual parameter is red or green or blue respectively, while scalar parameters occupy just 1 slot each. For example, this top mean height has an index of 5, and here it is. As I said, I do this gradient procedure twice to get 2 gradients, but they share some parameters. For example, I have 1 color parameter for both gradients, and 1 gradient contrast parameter, and so on. And then the result of the color interpolations goes into the switch parameter, and there's a general rule for shaders in UE5 to try to minimize the number of such switch parameters. But in this case I need it, and it is convenient in combination with displacement bake, which I showed earlier. So that covers ZGradient, and let's see what happens next. The third and last global function is the procedural snow. Here it is, and don't worry, right now this snow looks rather plain and unexpressive, and you may have noticed it lying on a flat surface which face normals pointing upwards, and you can also see some snow on bricks and everywhere on protruding micro surfaces. So this snow doesn't look convincing enough because I'm planning this to be more of a primer. On simple models where there will be very little snow, like stone flat walls, this quality will actually be enough. Let's open up the concept. See right here, if I want to make such indents, these small snow drifts, I will just add some lumps of snow made out of geometry. 1 or 2 of these models will be enough. At the same time, we have snow on the roof, and there's a lot of it here. It's piled up in clumps, We also have some borderline material like frost or thin ice layer on the shingles. So in the case of the roof, I will probably use snow as a separate layer in the material instance, because there it won't be enough to just use a procedural function. I will probably also add static meshes of snow on the roof, mixing individual snow clumps with a tessellated and displaced layer of snow from the material. Look, if in the case of walls I am reluctant to spend a whole layer on the snow, which in steep walls, barely exists, then in the roofing material I will definitely have only 3 layers so far. It's shingles, it's frost, and snow. Now back to the procedural function with snow. This is a method that is cheap, but performant and quick to implement. The feature is called UpVector Blend or Slope Blend, and it's quite ubiquitous in games development, particularly for moss, snow, dust, those substances that tend to lie on the very top of objects without really getting clogged into the crevices. So let's see how to work with this. I connect the function also through a switch parameter, and at the bottom I have groups of parameters that regulate the properties of the mask and the snow material itself. Let's set opacity to 1 and immediately we get our snow lying exclusively on the surfaces which normal vectors are facing upwards at this particular moment in the world. You see now we have a hard mask transition, and you can see it on the material ball better and on the column as well. The other parameters allow you to adjust the hardness of the mask, as well as the influence of texture baked normals on the model normals and on the mask. The column is not a good example for this, and later I will show how it will work on other objects. For now, let's just make the influence of texture normals visible. And here it comes out. You can see it clearly and better on the material ball. I've also gotten such thin strips of snow on the top of bricks, and to do this, I basically just increase the influence of the normal map as much as possible so that it shows through on such vertical surfaces. I also made the snow extremely white here, and let's tweak it to be lower. In general, by the rules of PBR, a pure snow white color is a value of 0.8, where 0 is black and 1 is white. We don't need pure snow here. It's more like we have a thin melted snow layer, a frosted stone even. So I do 0.65 for now, and then we'll come back to color calibration later. Next, what I often don't like in such procedural functions is the impossibility to influence the result with hands and correct some places to my liking. That's why I added this functionality. And let's go to the painting mode. If you remember, in our splat map, there is alpha channel in addition to RGB channels. Let's check this box and look. Now I can remove this snow by mask painting. If you want to return this snow, you will find that regardless of whether you paint or erase, the brush in the alpha channel will always erase the information by default. Here, I'm clicking both with Shift pressed and clicking without Shift pressed, and the result is the same. To fix this, I'm going to go right here to the alpha value and I'm going to put 0 in here. And now see, when I paint, I'm bringing back the snow deposits. And let me explain, we won't be able to mask paint snow everywhere we want with this feature. It's not required. This procedural snow layer is already bounded by an up vector or slope mask, and my alpha channel in the splat map serves the purpose of eliminating unnecessary snow on surfaces, either surfaces covered by roof, for example, or just to tweak the noise balance here and there. Let's take a little look at how this is done. Going into our master material again, we're done on the switch parameter of the ZGradient function, and after that, we basically keep complicating things with the base color attribute mostly. In both the ZGradient and the snow function, we're basically just adding additional colors, the solid colors, procedural colors, using special masks to blend them with whatever comes out as a result of layering. So here's our snow, parameter vector 3 for the color, lerping with the result of the previous switch parameter by alpha from the up vector function. And this function, up vector, is basically a mask that defines the white color depending on the direction of the 3D model normals, taking into account the combination of the face normals of the model as a base and the tangent normals we get from the textures. For the manual control I use the splat mask alpha channel. Here it is. In addition to color in the case of snow, I do a similar interpolation with the roughness attribute and then use another switch parameter. There are two nodes here, one adjusts the color and one adjusts the roughness, but they are similarly named. In fact, it's one parameter. The last function I haven't talked about yet, just to comment on everything in the graph, it's macro normal. I probably won't use it in this project, but in general, the concept of detail normal is generally required in any decent environment shader. I would use this normal map in cases where I have a huge, fancy shaped object that would benefit from having a macro normal and a micro normal. I won't dwell on this too much. Again, I hardly use it in our project, but you can easily find information about detail normal and different approaches to it on the internet, on the YouTube, wherever. To conclude the master material topic, let me say the following. Working as level environment artist, you will encounter different approaches, different features, different systems, but in general, all of them always have common origins, and if you practice working with shaders in Material Editor in Unreal Engine, it will help you to navigate in these different systems, at least at the level of competence necessary for 3D artists. As I said, I don't claim any particular correctness to my approaches. The tools you encounter will all tend to have strengths and weaknesses. For example, the ZGradient function was initially just a fun experiment. Instead, you can use something more interesting and advanced, like distance field based blending or macro color. But for my purpose, these systems that I showed works well enough. And finally, technology doesn't stand still. What may be true for July 2025 will be outdated information for July 2028, if not sooner. Unreal Engine is evolving, changing, just like other tools. But still, the logic of working with and building shaders for environment assets, including architecture, is an important element of our profession, even if sometimes we have no influence on it, because we don't write code. And nevertheless, as I said at the beginning of the video, the shader logic predetermines our entire pipeline and sets its pattern, if you will. Okay, here I'll stop rambling. Have a good day, and in the next video we will finally talk about modularity. I really want to share my most unpopular thoughts on this topic, so I hope you'll enjoy it.